The next talk is going to be given by John Pernet-Fisher from the University of Manchester, and he's going to be talking about Apollo granulite protoliths and using plagioclase trace element chemistry to investigate those. And I can see John is talking to us from the lab. How's that for dedication?
Analyses never finish. Hopefully, can you just full screen that? Can you see my slides okay?
Yep, you're good.
Smashing. Okay, well, thank you very much, Josh, and thank you everybody for tuning in today. So yes, I'm going to talk a little bit about granulites and specifically how we can use trace element chemistry and focusing on plagioclase trace element chemistry to see if they can say something about what the protoliths of these lunar metamorphic rocks are. So I'm going to start by just having a quick intro in terms of what the lunar granulite suite are exactly. I mean, they're not a particularly dominant lithology in the Apollo collection. They're mostly found at Apollo 16 and Apollo 17 landing sites, and there's a handful of well sort of characterized meteorites as well. But essentially, these are, as I just mentioned, metamorphic rocks that are the result of high temperature recrystallization of the crust. And so when I say high temperature, we're talking somewhere around 1000 to 1100 degrees C. The heat source for the granulites have been mostly argued in the literature to represent impact melt sheets. And so you can imagine a nice hot, thick impact melt sheet on the lunar surface that would provide the heat necessary to metamorphose the surrounding crustal rocks, although we'd like to point out that this effect could also potentially be seen surrounding basaltic magma chambers or any plutonic rocks that may be in the lunar crust, if you happen to believe the MG suite indeed do represent intrusive material. And so I've got a couple of nice just SEM backscatter images, sorry, just plotted here, just so you can see what sort of textures some of these samples look like. Typically, you see these really nice granoblastic type textures, as you can see on the image on the left. However, interestingly, in some samples in amongst this granoblastic texture, you do see these pockets of more poikilotic like looking textures that it's not really clear whether these represent relic textures of an igneous precursor, or if these, as some people have argued, represent little small blebs where partial melting has just started to occur in some of these samples where temperature have been sufficiently hot. But ultimately, the granulites, they represent the direct protoliths, the actual crustal rocks that underwent metamorphism, probably represent some sort of impact modified Highland lithology, so like an impact melt breccia. But ultimately, the granulites are sourced from, we think, from Highland lithologies, and so it's fans, the northosites, MG suite type material have come together in some kind of impact melt breccia through some sort of impact event, and they've then been metamorphosed. And I think trace elements have the potential, and what hopefully we'll argue in this talk is that they can sort of cut through and they can sort of investigate what some of these pristine igneous sources were for the lunar granulites. And if we can do that, this gives us an additional sort of piece of information to try and constrain the lithological and compositional diversity of the lunar highlands. Traditionally, you'll often see granulites referred to as ferroan or Magnesian. And this stems back to some of the first reported data from granulites that were mostly major element chemistry. And these, particularly in the early literature, have been used to argue whether they have more of a crustal northocytic affinity, or if they perhaps represent some sort of impact clastic rock that has more of a derivation from MG suite type lithologies. And we can see this, why people might come to this conclusion. If we look on the left, you've got the old classic plot of AN content in plagioclase versus magnesium number of mafic minerals. And you can see that, hopefully you can see my pointer, I'm not sure if you can or not. Some samples plot well within the crustal and northosite, the fan field, and others definitely look a lot more MG suite-like. However, hopefully what I'll show in the coming few slides is that this may not necessarily be the full picture. And so what can trace elements tell us? Well, the problem with major elements is that, particularly when we focus on minerals like plagioclase, is that they can be affected by subsolidus reequilibration. So when this thing's at temperature at high temperatures, things like iron and magnesium can move about a bit in the mineral. The advantage of the trace elements, and in particular plagioclase, is that they diffuse very slowly. So specifically things like the more incompatible trace elements, like the rare earths, they can take a very long time indeed for them to re-equilibrate. And so this is just a really sort of a graph to illustrate this point that if you had, say, 100 micron scale plagioclase at sort of temperatures that we're interested in terms of this type of metamorphism, it would take tens of thousands of years for neodymium to completely re-equilibrate within a plagioclase grain. And this is much longer than the sort of timescales of metamorphism or the equilibration timescales that we think the granulites have undergone. Most of the sort of published estimates for how long these rocks have been held at temperature for range from hundreds to thousands of years. And so in this way, the trace elements and specifically the rare earths have the potential to preserve some of their original igneous component, the composition of their original igneous components, and thus can give us a bit more of a detailed insight into the type of lithologies that are contributing to the protolith of the granulites. So, looking then at the trace element chemistry, these are analyses of plagioclase. These are chondrite normalized plots showing oil rare earths. And sort of for convenience, I've split these again into these sort of historic subdivisions of Magnesian granulites on the left and more Ferroan ones on the right. And the main thing really to take away from this plot is the range of plagioclase compositions that we find between these two suites. And so, you know, for instance, on the left, we see the magnesium granulites, while some look very similar to the compositions of plagioclase, rare earth compositions in plagioclase that have been reported from MG suite type material. It's this darker grey field in the background. While some of the magnesium granulites are similar to MG suite type plagioclases, many look a lot more anorthositic and a lot more trace element depleted. And this is even more so the case for some of the Ferroan samples. As you can all see, our Ferroan granulites range in composition from compositions that are very consistent with the most incompatible element depleted fan samples that have been reported in the literature, all the way to rare earth patterns that are a lot more MG suite like. And this variation, in fact, we can even see on really local levels. If we consider samples on the granulites on a per sample basis, and on a thin section scale even, you can see the range of compositions reported for individual thin sections. And so each of these lines on the screen represents a different plagioclase from the same thin section. And, you know, for some samples, for instance, there's one on the bottom left here, this Ferroan sample displays a really wide range of compositions indeed, from, again, more anorthositic like to more MG suite like. There's only really one sample that doesn't really show this sort of range of chemical heterogeneity. This top left sample, 79215, has got a fairly sort of tight range in compositions. It's a bit of an oddball sample in the sense that it's had a bit more of an unusual history. It's got some really large apatites in, and Alan Treeman has argued in a paper in 2010 that this may have undergone quite a lot of metasomatism and has had some sort of secondary alteration to that sample. But discounting that, in general, the sort of take home really from this slide is the sort of chemical, the very local scale chemical heterogeneity. And I think what this is telling us is that the sort of direct protolith of these granulites probably reflects a protolith that has a very sort of well mixed selection of highland lithologies. So again, coming back to this idea that the protoliths represent some sort of clastic rock that's got all sorts of different lithic components mixed in, and maybe some of the Ferroan samples have more of a sort of a dominance of anorthositic samples, whereas maybe some of the MG suite samples has more of a dominance of some of the Magnesian granulites may have more of a dominance from sort of MG suite type material, but nonetheless, both components are present. And I can sort of hammer this point home a bit more by considering other plots of trace elements. And so really, this is a plot showing europium over samarium, which is effectively a measure of the size of the europium anomaly in the rare earth plot, versus samarium, which in this case is just sort of representing how trace element enriched a sample is. And you can see that all the different sort of highland lithologies that have been found at the Apollo site have got quite distinct sort of fields. And so in this way, we can sort of use plots like this to try and hopefully sort of tease apart what are sort of the contributing lithologies to the protoliths of these granulites. And when we plot our trace element data, our granulite trace element data on these sorts of graphs, this sort of highlights once again this idea that we've got a mixture of different crustal lithologies in the protolith of the granulites. So again, we can look at the Ferroan samples. Some samples look very crustal and northocite-like. Other samples plot within the NG suite, and I see a similar picture for the more magnesium granulites. Curiously, though, and this is the last point I want to make really, is that some samples you can see lie outside the range of what's been reported for plagioclase compositions in the Apollo collection to date. So what could these samples represent? Well, these potentially give us some very sort of tantalizing glimpses at potentially some more unusual or more rarer highland lithologies that might be out there within the lunar crust. And so this was hinted at by Randy Korotev when he reported some bulk trace element data, and in particular he argued that some of the more magnesium-rich granulites represented compositions that were distinct from the Apollo MG suite type material. So you know, I think what we're seeing is a sort of a confirmation that some of these plagioclase trace element data are definitely revealing something that are a bit different. You know, whether this is a completely new lithology or whether it's just extending the range of compositions that the MG suite samples encompass still remains to be seen. But I think, you know, this is the main take-home message really from this talk, is that, you know, by looking at these granulites on a per mineral basis, and by looking at the trace elements of things like plagioclase, we can really start to look at some of the sort of the chemical compositions of a different set of highland lithologies that are out there, and sort of expands the range of samples available to understand what the compositional range and diversity of the highlands are. So I'll just leave that there really, just my conclusions, and just sort of say, just to sort of add to what I said before, you know, these traditional groupings of Mg versus more magnesium versus more magnesium rich may not be that helpful when we're looking at bulk elements, and that we really need to start picking apart these granulites a lot more to try and push forward our understanding of highland lunar geology. So I should leave that there. Thank you very much.
Thank you, John. We have some time for questions if anybody wants to ask John a question.
I was just typing a comment, but if I can, maybe I can ask a question, John. So you do get the prize for giving the presentation from a lab, for sure. This is the beauty of doing a virtual conference, that you can be so efficient. But I was just wondering, you know, you have done trace element work on plagioclases. I mean, surely you are also thinking about measuring some trace elements in associated phases to tease out those, you know, individual links that you were suggesting, especially those that were not following the Apollo trend, to see something else is going on.
Yes, yes. So we have got analyses from olivines and pyroxenes in the same sample. The slight challenge with the granulites is that they're a lot finer grained than the plagioclase. So particularly with our analytical setup, some of them were just too small, really. So, you know, definitely it's an important part of the story in terms of bringing in the pyroxenes and the olivines. But we've got some data, but certainly, you know, we won't stick it properly yet.
No, thanks. And at the start, you said that the temperatures were, you suggested a very narrow range of about 1,000 degrees to 1,100 degrees. I mean, does it have to be limited to that? I mean, temperature can be anywhere beyond that, right?
Well, yeah. So I guess these temperatures derive from thermometry that have been so people have taken sort of the classic sort of terrestrial 2-pyroxene thermometers, and they've applied that to the lunar granulites. And this is just the range that has been published in the literature so far, and we see a similar range for the samples that we've been investigating. But I mean, you're right. In principle, things could get hotter, and particularly when we start to look at these more poikilotic textures, and if these really are little blebs of partial melting, that would certainly imply hotter temperatures than that. But
I'm just going by what, you know, for example, you heard from Lee and Anna's talk, where they are talking about superheated melt sheet with, you know, 2,000 degrees plus temperature. So temperature to be around, but maybe not. Yeah.
Sorry, yeah, no, you're absolutely right. And we are actually doing some thermal modeling at the moment to explore what kind of temperature, if you do have a superheated melt sheet at like 2,000 degrees or so, we're doing some thermal models at the moment that hopefully we'll be publishing at some point soon to explore what sort of range of temperatures you can actually achieve in the crust.
Okay, thank you. I've taken enough time.